Okay, so now we've looked at two gas laws. Boyle's law, P1 V1 equals P2 V2, and Charles' law, V1 over T1 equals V2 over T2. Okay, so something I'm going to show you is I'm going to combine these. So I'm going to try to now, so remember, Boyle's law over here, this is for the situation where we're holding moles and temperature constant. Charles' law over here is when we're holding moles and pressure constant. What if we were only holding moles constant? Right? Now we're going to have to figure out how to fit all three of the variables, P, V, and T, all together in one equation so they all work. Now, the basic idea is if you're multiplying two things times each other, right, then you have a relationship that is inverse, right? Pressure goes up, volume goes down. That's what Boyle's law tells us. If you're dividing, if one's in the numerator then the other's in the denominator, then that means that they're direct. One goes up, the other has to go up. So let's start with Boyle's law, and then I'm just going to add temperature in. Okay, so temperature is directly related to volume. So I'm going to put T1 and T2 down here. So now we've combined them in a way that is consistent with Boyle's law and Charles' law. But there's a third sort of dynamic going on here we need to kind of check out and make sure it's okay. I am also saying that pressure and temperature are directly related, assuming we were holding volume constant, right? So think about this. What if I had an enclosed container like an aerosol can or something that I'm going to draw very poorly? Aerosol can. There we go. I've got a gas in there. What happens if I increase the temperature of that? What happens if I heat it up? The volume is now fixed. The volume is constant, but the pressure is free to change, right? The particles are going to start increasing their force. P equals F over A, right? This one's pretty easy. They're colliding with the container with a greater force, right? And the area isn't changing, right? The area is not going anywhere because the volume can't change. We're assuming that the can is strong enough it's not going to like bulge out or anything. So pressure has to go up, right? Temperature goes up, then pressure goes up at the same time. Temperature goes down, pressure goes down. So this works. Pressure and temperature are directly related. They very much are. And so you've probably heard of this, these sorts of compressed air canisters exploding under high temperatures because the pressure exceeds that the container can hold in. So this new gas law that I've written, I'm erasing it now only because I'm going to replace it with an electronic version of the same, is this. P1 V1 over T1 equals P2 V2 over T2. Now, if you can remember this, you can remember both Boyle's law and Charles' law, and even this other relationship. So this is the one you should memorize. And even this, I'm going to show you how you can actually find from something else. But if you want to memorize something, memorize this. P1 V1 over T1 equals P2 V2 over T2. The reason I say that you could find Boyle's law and Charles' law from this is, well, let me just show you how to do this. So, first I want you to try doing just this first one, and then I'll come back and I'll help you with this one, and then we'll do the second one. The second one is going to be sort of more interesting, and I'll show you kind of how, and it'll kind of lead into how you can find Boyle's law and Charles' law from the combined gas law. Okay. So this first one, so remember I've got P1 V1 over T1 equals P2 V2 over T2. So what am I solving for? I'm solving for volume in liters will it occupy in the second situation. So I'm solving for V2. V2 is going to equal, P2 is going to go down here, and T2 is going to go up here. no, T1 goes up there. And wait a minute, I screwed this up. Let's try it again. P1 V1 over T1. T2 goes up here. P2 goes down here. There, I got it that time. Okay, cool. So, all right. So let's just start solving. Let's just fill things in. So P1, the initial sample pressure, 755 millimeters of mercury, right? Times V1, which is 1.62 liters, times T2, not the initial temperature, but the final temperature. And remember, that has to be in Kelvin. So I'm going to take 50 plus 273 and get 323 Kelvin. Over P2, what's my final pressure? 725 millimeters of mercury, times the initial temperature, which is at 0 degrees C, right? And this illustrates very nicely why we have to use Kelvin temperature. Because the whole thing would go south pretty fast if I used 0 in the bottom, right? Right? I'd be dividing by 0, it becomes infinitely large, it becomes infinity. It just makes no real sense. So it's 273 because it's at 0. And then all I have to do, I have to make sure that all my units are the right units. Millimeters of mercury will cancel, Kelvin will cancel. And remember, pressure and volume can be whatever units you want as long as they match and cancel. Temperature is the only one that has to be a special unit. 1.62 times 323 divided by 725 divided by 2. I get how many significant figures? 3 significant figures. I get 2 millimeters of mercury. No, liters is my unit. So I'm solving for volume. Now, you may ask, why did I go 3 significant figures instead of 2 up here? And the answer is because first I added, right? I added 50 plus 273, and I got a 3 significant figure number here, right? It's this, because remember, we added first. Adding is all about decimal places, and then you multiply. When we multiply, then we look at significant figures. So I got 2 liters. Okay, so kind of while I'm erasing, you can start on the second problem. See if you can kind of figure that out. If you get stuck or just can't understand what I'm wanting you to do here, go ahead and start the video again. Okay, so on the second one, I have P1 V1 over T1 equals P2 V2 over T2. So let's kind of talk about this. I'm going to talk about it in kind of 2 different ways. So what am I solving for? I'm wanting the new pressure after we increase the temperature. So P2 equals P1 V1 over T1 times T2 over V2. Right? Okay, well, here's the thing. I don't have all these numbers. I'm going to plug in what I do have. Let's take a look. So P1, I definitely have 5.5 atmospheres. V1, I don't have V1. I don't know the volume. That's somewhat problematic. I have T2, my final temperature, so I'm going to take 35 plus 273 and get 308 Kelvin. And then on the bottom, I have T1, which is 21 plus 273. It's 294 Kelvin times, I don't have V2 either. This is a problem. However, here's the thing. This is a propane cylinder. It's a cylinder. We have a situation where the volume is constant, right? So if the volume is constant, if through this process the volume isn't changing, how does V1 compare to V2? Well, they're going to be equal, right? So I can actually drop the 1 and 2 labels and just call it V, if that would actually erase and stay erased. Then what happens is I get these cancel out. So because volume is staying constant, it drops out of the equation. Anything that isn't being changed drops out of the equation. And now we just take 5.5 atmospheres times 308 Kelvin divided by 294 Kelvin, and I get P2 equals 5.8, and my units must be atmospheres because that's the units that I have left over. So, where I'm going with all this is that you can figure out other gas laws from this combined gas law. So you don't need to memorize Boyle's law and Charles' law. They're embedded in the combined gas law. So here, if we look at this, actually this is not really what I wanted. I will have to come back to that. Sorry about that. I will just show you by hand then. So PV equals P1V1 over T1 equals P2 V2 over T2. So let's say I have a situation like in Boyle's law where pressure and volume are changing, right? But temperature is constant. Well, anything that's constant just goes away. So I'm left with P1 V1 equals P. I messed that up pretty good. P1 V1 equals P2 V2. So there's Boyle's law. Now let's go looking for Charles' law, right? In Charles' law, right? Charles' law involves volume and temperature changing, right? And pressure is constant. Well, if pressure is constant, it drops out of the equation, and I get V1 over T1 equals V2 over T2. So here's the thing. This is why I don't want you to know the names of Boyle's law and Charles' law. They're not really relevant. I don't want you to memorize Boyle's law and Charles' law. I want you to know, instead, looking at the combined gas law, I want you to say, okay, well, in my problem, in my question that I'm being asked, where I have one situation and then the gas changes and there's another situation, this particular variable is being held constant, like volume. Well, then it drops out of the gas law. It just isn't involved in the combined gas law. It just goes away as long as it's being held constant, because V1 and V2 now are just V and they cancel each other out. So, really just memorize the combined gas law, not Boyle's and Charles'.